Okay, with our coding method, we find a direct proof for the rate distortion function. So an attributability proof for it. Now we want to know if this is the best possible. Perhaps we can compress the data with the same distortion more. And we will show now that our method is also optimal. But to show this, we first want to show that our function we got by the direct proof, we defined it to be R of D, is convex. What does it mean that it is convex? So that means we take two distinct points, D1 and R of D1, D2 and R of D2, and suppose that this channel achieves the points. Now you see in the picture what does it mean? We have these 2 points, and when it's convex, that means the point in the middle lies below this line here. So let's assume that the channels x tilde 1x and x tilde 2x achieves these points D1 and D2. That means D1 is equal to the expected value of the distortion of x and x1, and R of D1 is exactly then the mutual information between x and x1 hat, and D2 is the expected value of this distortion here, and R D2 is exactly the mutual information of x and x2 hat, because these 2 channels exactly achieves this rate. Now we consider a thought distribution, Px Vx, which is lambda times Px tilde Px hat 1 under the condition x plus 1 minus lambda Px hat 2 under the condition x. And we define D3 as this point here, Px times this distribution times the distortion here. And of course, for this distribution, we can insert here this setting. And then we know that D3 is equal to lambda times D1 plus 1 minus lambda D2. Now we want to consider the rate of this point. The rate of lambda D1 plus 1 minus lambda D2 is equal R D3, as we show. And now this R D3, we do not know if the distribution Px3 is optimal. So we have here lesser equal. That's lesser equal to the mutual information between x and x3 hat, because perhaps there is a better distribution. Now we use that the mutual information is convex. So we can write the mutual information as lambda times the mutual information between x and x1 plus 1 minus lambda the mutual information between x and x2. But this we know is equal to R of D1, and this is equal to R of D2. And that's exactly what we want to have. So we know that R of D is convex in D.